On December 2nd, 1942, man achieved here the first self-sustaining chain reaction and thereby initiated the controlled release of nuclear energy. We opened a great new field of research. We released for our controlled use a tremendous source of energy. We gave ourselves the means for investigating life and the life processes. We gave ourselves the means for learning about the very structure of matter, the very foundations of nature. Today in our country, men and women are studying the atom and its uses. They are studying and working in research centers and laboratories across the nation. Some of the laboratories, like this one in New Jersey, are operated directly by our national government. Others, like this one at Oak Ridge, Tennessee, are operated by private industry. In many educational institutions, like this one in California, there are laboratories in which atomic research is carried on. And here in Washington, D.C., is the headquarters of the United States Atomic Energy Commission. Here, the work of planning and unifying and evaluating our atomic research program is carried on. What is being done in atomic research? Atomic research can be divided into three general areas: studying the energy applications of nuclear fission, learning about the structure of the atom, especially its nucleus, and making use of some of the byproducts of nuclear fission. Let's look first at the area of atomic research concerned with energy. This is an atomic bomb, a chain reaction, out of control, releasing a great amount of energy. This large concrete box-like structure is an atomic pile. Inside this atomic pile, a chain reaction takes place, under control. Unlike the atomic bomb, the atomic pile does not explode, but instead, its energy is harnessed. So we can control the energy the atomic pile releases and make use of it. There is the promise that the energy of reaction may be used to heat and light whole cities, economically, without smoke or dust. Factories may be run by atomic energy. This is the hope of the future. We have already learned how to produce small amounts of electricity from atomic energy. We are learning now how to power ships and submarines with atomic energy, and we have just begun. Things we learn to do in this area of atomic research may add much to the progress of civilization. Let's look now at the area of research that is concerned with the structure of the atom and its parts. This is a cyclotron. It's one of a number of devices, sometimes called atom smashers. They don't really smash atoms, but simply dislodge particles from the nucleus. They're helping scientists learn how matter is put together. The answers are often in the form of complicated mathematical formulas and diagrams. Often, electronic calculating machines doing the work of hundreds of mathematicians must be used to help find and test the answers. This scientist at work in the control room of a cyclotron is also helping to find the answers. It was exactly this sort of basic research that led to the release of atomic energy. It is this research going on today that may open up great new fields of knowledge for practical use by future generations. The third area of atomic research is concerned with making use of the byproducts of nuclear fission. Let's see what they are and how they are being put to use. Here is an atomic pile again on the left. A chain reaction is going on inside it, producing something called radiation. Radiation is dangerous, but the men who work about the pile are protected by its thick walls. The radiation can't get to them. But when certain materials are put inside the walls of the pile, closer to the chain reaction, they absorb the radiations and become radioactive. Some materials are naturally that way. If your alarm clock glows in the dark, it's probably because a radium paint has been used on the hands and numbers. Radium is naturally radioactive. The material that you see coming out of the pile has been made radioactive. Like radium, it will give off rays that can be detected with sensitive instruments. This new radioactive material is a byproduct of nuclear fission. The rays that it gives off, like the rays of radium and X-rays in large quantities, are dangerous. Lead can stop the rays, so the radioactive material must be carried in heavy lead containers. And when scientists experiment with these materials, they use remote control devices. But these materials that are dangerous because they have been made radioactive have provided science with a new tool of tremendous value. And so these byproducts of nuclear fission are packaged and shipped to laboratories all over the country, where they are being put to work for science. Let's see. Inside these flasks, tiny plants are growing in water and a solution of carbon dioxide. Light is coming from beneath. The plants are producing food from these ingredients by photosynthesis, a process that has long baffled scientists. But now they are able to gather information about the process that no microscope has ever been able to show. This is how. The carbon dioxide that they add has radioactive carbon atoms in it. These atoms are called tagged atoms because their radioactivity is a sort of tag by which these atoms can be identified. Photosynthesis is taking place in the plants growing in the flask, and tagged atoms are being used in the process. Scientists can follow them and learn just what changes take place in the photosynthesis process. Later, when the plants have been prepared for study, the scientists, using sensitive instruments, search for the tagged atoms. In a sense, these atoms report from inside the plant. They are helping scientists understand the process of photosynthesis. Someday we may be able to manufacture food just as plants do. Tagged atoms are also helping farmers put fertilizers to better use. Fertilizers with radioactive substances in them are added to experimental soils. Later, in laboratory greenhouses, seeds are planted in these prepared soils. The plants that grow from these seeds will absorb the radioactive fertilizer materials that are in the soil. When the plants have grown, the radioactive atoms, the tagged atoms, have become part of them, and scientists can detect tagged atoms. In the laboratory, these plants are processed and formed into these cylinders, which then are studied. The tagged atoms that report from inside the plant let the scientist know how the plant has made use of the fertilizer. This knowledge will help farmers make more effective and economical use of fertilizers. The process of egg formation has also been studied. Radioactive substances were fed to the hen that laid this egg. They are now a part of the egg, part of its shell and yolk and albumin. After the egg has been prepared for study, these radioactive substances report from inside the egg, letting scientists know how certain minerals were made use of in the egg's formation. This basic research has given important information on the proper diet for chickens. Tagged atoms are being used in industry. In the steel-making process, for instance, we are getting reports from inside molten steel. Some of the atoms of one of the ingredients are made radioactive. Then these atoms are followed to determine the best means of putting the various ingredients of steel together. This will help us make better steel at lower cost. Oil fields can be charted with the help of tagged atoms. When they are pumped down oil wells, they spread throughout the underground oil field. Instruments can follow their movements through the oil. The underground fields can be charted. In the field of medicine, tagged atoms are being used to help doctors detect and treat certain diseases. Materials that have been made radioactive are being injected into this man's body. These materials will report from inside, and the doctor, using a detecting instrument, will learn how well certain parts of this man's body are functioning. Substances which have been made radioactive are being used to treat patients with certain types of cancer. In the glass is a solution of radioactive iodine. The iodine will soon concentrate in the cancerous thyroid gland in this patient's body. There, the rays that are given off, like the rays of radium, will help to destroy the cancer. This is another one of the many ways byproducts of nuclear fission are being put to work for our benefit. A few of the many activities now going on in the areas of atomic research. And there are many activities, for remember, this is a new man-made world of tremendous promise, largely unexplored, barely tapped. Great numbers of men and women are needed. They are needed to help us explore the energy applications of nuclear fission, to help us learn about the structure of the atom, to help us make use of the byproducts of nuclear fission. Today, there is work that awaits us in medicine, in physics and chemistry, in agriculture, in engineering. New devices must be developed, new buildings designed. And there is work in related areas, in countless related areas into which atomic research is expanding and will expand for the benefit of mankind.